Hello students, welcome you all in fourth lecture of chapter 13 magnetic effect of electric current. Till now we studied about electric motor and now the next topic is Faraday law. In this lecture we are going to study Faraday law, its observation, electromagnetic induction and little bit we are going to about AC generator, or you can say generator, and Fleming right hand rule we are also discussing. So four topics we have in this lecture. So EMI, electromagnetic induction, is a process in which electric current will induce around or in a coil, you can say in a coil, when magnetic field will change. Magnetic field will change around that coil. Okay, so we will discuss in detail. First we are going to study about Faraday law, then you get to know what is EMI in detail. So this is electromagnetic induction. Electromagnetic induction. So let us start with Faraday law first. Faraday law or Faraday activity, you can say. Faraday did three activity, and from that he concludes to two laws. He gives us two laws. So Faraday activity, in this we have that suppose this is a coil we have, and this coil is connected with a galvanometer. What is galvanometer? Galvanometer is a device which is used to detect the current in a coil. You can see even it can signifies the direction of current, because galvanometer can show deflection in both the direction, right side as well as left side. And the next thing, it can calculate the current galvanometer for a very small value, micro or milli as well. Okay, so we just suppose this is a bar magnet we have, north and south pole. So as we take our bar magnet nearby to the coil or far away from the coil, the amount of magnetic field will change in this coil. Okay, and this change in magnetic field will cause some current will induced. Okay, let me show you a situation. Suppose here is our bar magnet north south. Here is our bar magnet north south. Here is our bar magnet north south. This is position 1, position 2 and position 3. We have three places where we put our bar magnet. So at this point the magnetic field is having a certain reason. At this point magnetic field having a certain reason. At this point magnetic field having a certain reason. But this magnetic field is very much close to the coil. This point magnetic field is not so much close. It means at this point the strength of magnetic field, at this point the strength of magnetic field, they are different. So this change in magnetic field per unit area nearby a coil, this change in magnetic field per unit area nearby a coil will cause to induced a current in that coil. Let me check the frame. Yes, it's clear. So in all these three places the magnetic field lines or magnetic field, you can say, will change, and this change is known as magnetic flux. This is known as magnetic flux. Number of magnetic field lines per unit area. So at this point we have less number of magnetic field lines per unit area because it is very far. Now a little bit more, now maximum. So as the place will change, the number of magnetic field lines per unit area will change, and this change in number of magnetic field lines per unit area will causes induced current in the coil. Okay, so directly now we can say whenever there is some change in magnetic flux, we are getting some induced current in the coil. And what is magnetic flux? Number of magnetic field lines per unit area. More will be the number of magnetic field lines, it's okay, but change. So when we get induced current. When we get induced current, when change in magnetic flux. This symbol is for magnetic flux. This symbol is for phi. This is known as phi, phi. So whenever there is some change in magnetic flux, then current will induced, you can say, with respect to time. Obviously, this magnet will take time to come from this place to this place, this place to this place. So whenever there is some change in magnetic flux with respect to time, we are getting some current. So this is very first activity of Faraday. In this activity, Faraday took the magnet nearby the coil and observed the galvanometer, needle of galvanometer will start deflecting. जो सुई लगी हुई थी inside the galvanometer, that will start deflecting, and galvanometer will respond only for electric current. It means there is some current, and from where that current comes? That current comes from the induced current when change in flux, when change in magnetic flux, when change in magnetic flux with respect to time. With respect to time. This is very first activity. And second, in second activity, what he did, he again take the same coil which is connect with the galvanometer, and now he place a coil instead of a magnet. With again you can take same situation, same position 1, 2 and 3. Different positions. Means either we can use a magnet or we can use a coil. They both are, obviously we know very well, whenever some current will pass through a coil, it will generate a magnetic field. So due to this, again we get a magnetic field, and due to different positions, when we are moving the coil towards this one or away from this one, definitely number of magnetic field lines per unit area will change with respect to time. So due to this change, again the galvanometer needle will start deflecting. Okay, but the difference is when we are moving towards, it will deflect in this direction. Okay, when we are going away, it will deflect in this direction. It's an example. It depends on the north pole or south pole. Okay, you can do the same like this. If you change the polarity, means if you did like this, this is south, this is north, this is south, this is north, this is south, this is north. So now what happens? If in this case, when we are moving towards the coil and deflection in this direction, what is this? Anti-clockwise direction. So now when we are moving in this direction, now deflection in, yes, clockwise direction. So it also depends on the poles. It also depends on the poles. Is it clear? So the thing is, whenever there is some change in magnetic flux around a coil, the current will induced with this. The current will induced in the corresponding coil. And the third activity, which this Faraday did, noted down. Then I erase it. Okay. Now the third activity is. The third is we just place the same situation, we just take the same situation that this is a coil, okay, and this is attached with a galvanometer, and now he placed a coil over here. Like this. Now this coil is not moving. This coil is not moving. Okay, but still, is it any deflection over galvanometer? No, because there is no magnetic field. But as soon as we connect this, there is some current in the coil, and due to this current, magnetic field will be generated. And earlier magnetic field will be 0. Just remember the thing. Let me do the same. Here we have such situation. This situation we have, and in this situation, any magnetic field is here? No. Any magnetic field? No. And now as we connect this, the current will flow in the coil, and whenever there is a current in the coil, we are getting magnetic field. we have some magnetic field. Initially we don't have magnetic field. So what happens? Change in magnetic field per unit area with respect to time. So it means we are getting some deflection. But this deflection is for a moment, for a moment you can say, for a very small interval of time. एक बार हल्का सा डिफ्लेक्शन दिखेगा and that's fine. Okay, why? Because now regularly we are giving current to the coil, regularly we are getting magnetic field, so amount of magnetic field remains same. First there is no magnetic field. Second, there is a magnetic field. Third, there is a constant magnetic field. Now when magnetic field is constant, because current is constant, so now when there is a constant magnetic field, so there is no change in the needle. Because there is no change in magnetic field, no current will induce, so galvanometer needle will move back to its initial position, because now there is no current. So it means now the conclusion Faraday laws, first Faraday law says, whenever there is some change in magnetic field, note it down, whenever there is some change, whenever there is some change in flux. I think you know it very well. Flux is magnetic field lines per unit area. So whenever there is some change in flux, current will induced in the corresponding coil. Okay, and second law is, okay, one more thing beta, in some books it is found this word EMF. What is this? Electromotive force. Okay, so in few books you found that whenever there is some change in magnetic flux, EMF will induced. What is EMF now? EMF is just a force which pushes electron in a conducting body, and you know it very well from chapter 12 of the same class 10th that whenever there is some electrons are moving in a conducting body, then we get current. So what is EMF? Electromotive force. It is a type of force which pushes electron and we are getting current. So directly I told you that whenever there is some change in flux, current will be induced in the corresponding coil. Okay, now the second point is EMF or induced current is directly proportional to amount of flux. More will be the change in flux, more will be the induced current, or it also follow direction reverse. It also follow direction reverse. It means, if as I in first example I show you that the direction of magnetic flux will change. Direction of induced current will also change. So note it down. We have two laws. Okay, done. So next beta. Okay, one more thing I can tell you that factors. Okay, let me write over here. I erase this diagram. Factors on which induced current. Okay, for your simplicity I write ID. Induced current. I is the symbol of current, and induced. Okay, so I लेता हूँ. Induced current. Okay, induced current. Factor on which induced current depend. So firstly, it depends on is equal to induced current will depend on flux. More will be the flux, more will be the induced current. Okay, और you can ये तो आप लिख चुके हो, आप ऐसा लिखो induced current will depend on magnetic field. Magnetic field, more strong is magnetic field, more strong we are getting induced current. Okay, next it depends on area. It depends on area. Okay, area, which area? Beta, the formula is E is equal to d phi by dt minus, what is this E? Now you are familiar with E, electromotive force. What is this phi? Magnetic flux. So change in magnetic flux with respect to time is induced EMF. We did this, and EMF is equal to BA cos theta. This formula is from class 12, so don't worry about it. And this is from class 12. I just tell you just for your knowledge. So on which factors it depends? Induced current depends on magnetic field and area of cross section. Area of cross section, and third is the angle. Third is the angle. Angle between magnetic field and area. Magnetic field and area. Why? Which area is this? That particular area where we are going to calculate number of magnetic field lines. Remember that word when I told you what is phi? Number of magnetic field lines per unit area. So that area I am talking here. That area. What is flux? I write, I think already. Yes, number of magnetic field lines per unit area. So whatever be the area of cross section we are taking, that at this point how many magnetic field lines, so that area I am talking here. ठीक है ना? More will be the area और less will be the area, directly proportional है EMF की, magnetic field directly proportional, theta directly proportional है. ठीक है ना? Okay. So this is about, मैं एक बार रिपीट कर देता हूँ, ये बहुत इजीली समझ नहीं आता है बच्चों को. Actually क्या, the laws are whenever there is some change in flux we are getting current, or you can say we are getting EMF. What is EMF? Electromotive force, which helps to move electron, which apply force on electrons so that electrons are moving. Okay, when electrons are moving we are getting current. Okay, and this is induced current. This is induced current, and induced current is directly proportional to phi, and it also follow, this is our previous statement, and it also follow direction reverse. Direction reverse means if the direction of magnetic field will change, then direction of current will change. As I show you in the activity, when magnet is moving in this direction, deflection is anti-clockwise. When magnet is moving in this direction, deflection is clockwise. It means that it also follow direction reverse. And factors on which induced current depends. Induced current depends on magnetic field. More will be the magnetic field per unit area. It means more will be the induced current. More area we are taken, then definitely the EMF will be more. And angle, which angle? Between magnetic field and area. Magnetic field and area. Okay. Okay. This is about Faraday laws and on which factors the EMF, or you can say the induced current, will depend. Note it down so that we move to next. Okay, next is beta Fleming right hand rule. Fleming right hand rule. Actually, as we did Fleming left hand rule, we have to point out our thumb, first finger, middle finger in such a way so that they are perpendicular to each other. Similarly, now here also we point out our first finger, middle finger and thumb in such a way so that they are giving same direction of magnetic field, direction of force, or you can say direction of motion, and direction of induced current. Fleming right hand rule is used for induced current. Fleming left hand rule for use normal current which we are giving, and this right hand rule is used for that current which we are generating, which we are inducing, which we are taking, which is developed Okay, so Fleming right hand rule. Fleming right hand rule. In this view again also we point out our thumb, first finger, middle finger in such a way so that they are mutually perpendicular to each other. Father, mother, child. But this time this father is direction of motion, because now we are moving our magnet, we are moving our coil according to Faraday activity. Okay, so this is direction of motion. This is not force. This is direction of motion, and this is direction of magnetic field. And what is this? What is this? Direction of induced current. Okay. So first finger, middle finger, and thumb. First finger direction of tells us about direction of magnetic field. Similarly, middle finger tells us about the direction of induced current. Direction of induced current. Okay, it's for your simplicity. ऐसा कोई symbol नहीं होता induced current. Okay, thumb. This is direction of motion. Which motion? In which direction, or in which direction our magnet is moving? That is direction of motion. Okay, we did the same thing in our electric generator. Okay, so just note it down. Same you can apply a little bit same. Father, mother, child. Father, mother, child. This time this child is not current. This is induced current. This is same magnetic field, and this is direction of motion. Direction of motion. So this part is same in both. That logic which I gave you, father, mother, child. This is direction of induced current. This is direction of magnetic field, and this is direction of motion, not force. This is direction of motion of our magnet, which is moving. Okay, so note it down. Okay, so let's move to next, that is AC generator. AC generator is having the same, almost same you can say, or the only difference between the AC generator, or you can say generator and motor. Okay, generator and motor, the main difference is in generator we are getting electrical energy and we are giving mechanical energy, but in motor we are giving electrical energy and we are taking back mechanical energy. This is the only difference. Generator, we have two types of generator, AC generator and DC generator. Okay, that's enough for this lecture. Let's move to the rest part we did in next lecture. Thank you so much.